So very good afternoon, everyone. And we have a very special lecture and given by a very special person, Professor Reji Philip, who has got a profound interest in audio and audio signal processing and home breathing of electronics. And I think in my memory, as far as my memory goes, this is one of the first time we have an audio-related talk in this auditorium, probably after Professor Raman, who used to be always fond of music. Okay, without me saying much, and we also have special invitees and special people, the summer school students, Spectra 2023 students are here. As you will see, they are occupying most of the place our faculties used to take, and I think they are going to be the future ones here anyway. So thank you, Professor Reji.
I should thank you all for enthusiastically taking part in this, and I hope you've learned things which will be really important for you in the years ahead. You'll remember RRI and come back as whatever interns and graduate students.
So thank you, Professor Tarun.
So thanks a lot, Prabhu, for the kind words, and I'm extremely happy to actually give this talk here, because usually, we speak only about the research work that we do and a lot of nonlinear optics and plasmas and all that, but you hardly happen to speak about your hobby. So now the right opportunity came, and I sincerely thank Rekhu and Prabhu for giving me this opportunity here to speak to you. This originated as, in fact, as a talk for our young guys here, the future kids, so who are attending our practical electronics program. But when I went through the details of this talk, I really found that, okay, there can be a larger audience for this, because everybody is interested in audio, music, everybody is interested in movies, so therefore, why not? So that's why eventually this happened like this, and I'm very happy to see the full house here, so everybody is interested in music and movies. So the title of today's talk is From the Phonograph to the Phone, the History and Technology of High Fidelity Sound Reproduction. So let's see what we have here. The contents of this talk will be, I'll start by telling you about recording, playback, and a bit of broadcasting, and the historical perspectives of this, the analog era and also the digital era, then the audio system components and topologies. We have preamplifiers, tone controls, equalizers, power amplifiers, everything. Different classes, class A, class B, class D, many things are there. So it won't be possible to touch upon everything because time is very limited. In 1 hour, you cannot say even a fraction of what literature and what stuff exists there. Anyway, but I'll try to say as much as I can. And then we have speaker systems, which are a very important part of any audio system. There are various ways in which you can configure your speakers, then power supplies, ground loops, circuit grounding, home theaters, the comeback of disc records and tube or valve amplifiers in these days. So everything will be a little bit of all that. That is what I would like to say today. So coming to the essence of hearing, how do we hear? We have the ear, and that is, if we can call the preamp of the ear there, and you have an auditory canal there, and whatever the antenna is here, this is the antenna, which actually collects all the sound, all the voice, all the noise, everything, and then it goes through the auditory canal, and finally the brain processes. And this is an extremely sensitive organ of the body. That is what we have to appreciate, because if you look at it, the ear has incredible sensitivity and incredible dynamic range. So the sensitivity is like the threshold of hearing, if we call that I0, that is like less than 1 billionth of atmospheric pressure. The rustling of leaves, for instance. In a very silent room, you can hear a pin dropping to the floor. So that's the kind of sensitivity the ear has. And now what is the upper limit? The upper limit is the threshold of pain that is 10 to the power 13 times of the threshold of hearing. Now look at the dynamic range of the human ear. No electronic device, I think, can have this kind of a dynamic range. It's impossible. And the audible frequency range extends from 20 hertz to 20 kilohertz, even though adults can never hear anything beyond 15 kilohertz also, because as we age, the tympanum of the ear becomes thicker, and when it's become thicker and thicker, it cannot really vibrate at the higher frequencies. So only infants and babies can hear the high frequencies close to 20 kilohertz. So I think there is a demo of this in the for our younger friends in the EG labs, and also it was there when we had our annual day. So you set up that, I remember. So you can actually test your hearing ability and see up to what frequency you can hear. So that is the way it is. However, electronic systems usually are made, these audio systems are usually made for specifications up to 20 kilohertz, and that means the bandwidth will exceed that. Usually it can go to 100 kilohertz or something. So you have to be careful about oscillations though. We will see all that. So in this frequency range, we have a lot of stuff. In the very low frequencies, that is called the bass frequencies, and the low bass, that is where in the movies you have the LFE region, that is low frequency effects, like bombs exploding, helicopters flying, and all that kind of sound actually comes through the subwoofer, which is specially made for amplifying the very low frequencies. And then you have the human speech. And then you have all the musical instruments, music itself, and the cymbal and that kind of things. Actually, they make the treble sound, and they are on the high frequency side. So an ideal music system has to reproduce all these frequencies faithfully without any distortion. So that's the ultimate goal of high fidelity. Now, these curves are important in audio. These are known as equal loudness contours, known as the Fletcher-Munson curves. So what it shows us is that the ear is most sensitive to the 3 to 4 kilohertz region, which is associated with the resonance of the auditory canal. So the auditory canal has a resonance in that region. So therefore, even if you have a little sound there, you will hear it. On the other hand, when the frequency goes down, when you go to the bass frequencies, it is necessary that you need more pressure, more air pressure should be there for us to hear that. So this is the equal loudness contour, and at different power levels, actually the contour changes shape. At very high powers, like 100 fonts, I mean it's like 100 dB in some sense, there, where it's extremely loud, the contour becomes flattened. But at very low levels, or reasonably low levels, that is usually the level at which we hear music at home. At those levels, this contour, as you can see, is very non-uniform, and therefore, let us say you want to enjoy music at low volume, that's what we normally do, then you have to have really, really good bass frequency reproduction. That means you have to have very good subwoofers. Otherwise, at low volume, it is very hard to hear those frequencies. And in the music system, naturally, most of the power is spent for amplifying the low frequency region. And the voiced speech, the voice of a typical adult male will have a fundamental frequency somewhere between 85 to 155 hertz. And for a female, for the adult female, this is slightly higher. It is from 165 to 255 hertz. So that's the reason for the difference in pitch between the voices of adult males and females. Now, coming to music, we know that basically music is composed of all the tones, sa re ga ma, and all that. So this is divided into several octaves. And what is an octave? In an octave, the fundamental note and its second harmonic are exactly double. So this is divided into 7 notes in music, both in Western and Eastern, sa re ga ma pa da ni. And then the same thing repeats at exactly the double frequency. So this is, but nevertheless, there is a small difference between the frequencies between the Indian and Western classical styles. So in the Indian, you can see the sa starts at 262 hertz. Of course, you can have an octave lower to that, but this is usually where this is 1 octave, 262, and the ni is at 490 hertz. If you compare, it starts at 261.6, in Western music for the piano, and then it ends at 493.9 for the Western piano. So this is a small difference, and normally not of much consequence, because in any case, when you have an orchestra, you will tune all the instruments according to the bass piano. And for the keyboard, people don't usually take pianos for normal orchestras. So the piano has 7 1/4 octaves, and it has 88 keys, and the range is very large, from 27.5 hertz up to 4186 hertz. This will completely contain all the human notes. I mean, no singer can sing below this or above this. So let's look at the historical perspectives of sound recording. What came first was something called the phonograph, and it was in the 1850s. So this French man by the name Leon Scott, he developed the phonograph in the 1850s. And the sole purpose of this was, it was not meant for reproducing any sound. The whole purpose was to visually record the vibrations of the voice so that they could be studied by those involved, those studying human speech, those studying acoustics. So this was meant for them. Even Leon Scott never imagined that he could use it for reproducing sound. He just recorded them and looked at the pattern and all that. So what he did was, the vibration, so this is a kind of instrument, as you can see here. So there's a drum-like thing. It's a megaphone. And then you speak at one end of this, and at the other end, there is something that vibrates, and a thin diaphragm, and a thin brush is attached to this thin diaphragm, and the brush vibrates, and that vibrates over a glass plate which is coated with lampblack. So on that lampblack, patterns will develop. So this is the original pattern from one of his, some of these slides have been recovered actually, and they have been played back. That is the interesting part of it. In 2008, scientists actually played back the phonograph, which the inventor never imagined. So I have a hyperlink. I will try to play that. Let us see. Great. Yeah. Hear this. Thank you. This is the original sound recording of those days. Oh, actually, Leon Scott is singing. He's singing. Yes. Yeah. It's actually he's singing. Yes. So, so that was the first recording which was reproduced back in 2008. And then things were much better after this. So now Edison, he recorded sound on tin foils. So that was a very first medium in which something legible could be recorded. And around 1877, and he played them back. He called this instrument talking machine, because it was very wonderful in those days, because there was no instrument that could talk back to you. So this was a talking machine, and the recording was vertical in the sense that it was recorded on grooves, and these grooves, when the sound was louder, it had more depth, and when it was not loud, it was shallow. So this had a problem. This kind of a recording has the problem that when you have a low note, when the voice is small, the needle can actually get out of the groove, because it's at the top and it can easily skid and go out. So this was a problem, and they were trying to solve these issues, and he actually started using wax cylinders. So the tin foil was not really very good. So he started using the wax cylinders after that, and for recording, and he named this device the phonograph in 1887. And Edison was actually an excellent businessman also. So he would make excellent advertisements for all his devices, whatever he made. And then, he was very interested in making all of them in a very artistic way. So you can see the phonograph there. So this is a phonograph. So this kind of artistic making of something, of electronic stuff in particular, doesn't exist anymore. So these wax cylinders, so these machines, actually they were very good. I mean, you can hear, at least, it's a military band. Military band, yeah. Yeah, so that's what Edison could manage. So remember, these were times when there was no electricity. So in fact, at the same time Edison was trying to develop his audio systems and all that, he got another contract for electrifying the entire New York City. So he was after that, because that was, of course, that was more money and so more useful maybe to the public than something like than the phonograph. And so he was busy with that, and several people actually at this time tried to develop the talking machine to higher levels. And this was the acoustic recording before electricity. So up to 1925, this was the situation. So symphonies and all those things were recorded on wax cylinders, but then round cylindrical wax cylinders. But they used big acoustic horns like this, so that you have to stand in front of it, you have to sing, and then just because of your throat pressure, the ability of your throat, it will get recorded on the foil, or on the wax cylinders. So, I mean, you could not sing softly or anything, it just won't get recorded. And not only that, for making multiple recordings, they had to do this again and again. So I've read about a singer, one of the famous singers of those days, who actually did the same song 50 times a day. And you have to sing very loudly, 50 times a day. So there are no masters, no master record using which you can make prints or copies. So that was the situation in those days. And some of these acoustic recordings are still available. I mean, you can look for them in the internet and you can get them. They are there. And they actually sound pretty nice. And now comes, from the phonograph, we are going into the gramophone. So this is what we have here. So Prabhu has been very kind to bring this. This is actually the record player, the next version of the gramophone, because this is electric. And we will show this during the demo time. So the gramophone actually was invented by somebody by the name Emil Berliner from Washington. And he took patent for the gramophone in 1887. So the big change here was that instead of recording on wax cylinders, this became a flat thing. So you have a disc here. It is not a cylinder anymore. You know, it's very difficult to keep cylinders. You have to, it's this size and all that. So you have to keep it somewhere and takes more space. This guy is very flat. It doesn't really take that much space and all, very convenient and all that. So, and the first record disc was actually made of zinc. It was zinc actually. And it played on a turntable using a steel stylus, steel. However, and the recording was lateral, you know, it's not vertical recording, it is lateral recording now. The depth is the same. So this movement of the stylus actually gives rise to the sound that comes out. So this was a better kind of recording. And zinc, anyway, was later replaced by shellac. So the first kind of records that actually reached India from England, they were all shellac actually. I don't think anybody really has wax cylinders and zinc records in India. But shellac records many people still have. They used to run at 78 RPM, the very first kind of records. And this is some of the advertisements that appeared in the media in those days, newspapers and all that. You know, I mean, the kind of, Edison himself used to write these sentences like, the phonograph has brought happiness to thousands. So these are the kind of, you know, advertisements, and they were selling a lot. Like you can see, like it happens even now in the shops there were different sections for different companies. You know, this is a section for Edison, and you can see several phonographs sitting there for sale. And this was a situation, many people bought it. And so the gramophone is advertised by Berliner here. So like that. And the further development, the phonograph did not develop because the wax cylinder and all that, but the gramophone actually developed. So the original one, 78 RPM, shellac disc, running very fast, rotates pretty fast at 78 rotations per minute. And then they were noisy actually. I mean, I still remember having this at home in my childhood. Now, no idea where the machine is. Just one song on one side of the record. You can have maximum 2 songs on this, which is this big, and noisy also, very noisy. Electric recording comes in 1925, and then the record player, of course, with electronic amplification and things like that. Then you have smaller speeds, 45 RPM and 33 and 1/3. So that is the actual speed, 33 and 1/3 rotations per minute. So this record which is here, which is sitting here, is actually this 33 and 1/3 record. So that's the speed of this record plate, and that became the standard later on, as long as it was in use. And then these are called LP, vinyl. The material also changed. It's not shellac anymore. Shellac is brittle. If it falls down, it will break. Vinyl is little more safer. And this is called the long play record, LP record. And it could contain something like 20 to 25 minutes of music on either side. So in total, I mean, 25 minutes of music means like 6 songs or something. So in total, these records could actually contain about 12 songs. Compare that to the CD in MP3 now, which can contain maybe 200 songs. So, but I'm coming to that. There are some prices that we pay for doing that. And then the LP stereo came in 1958. So they used both vertical and lateral here for having 2 channels. So the stereo channels came in 1958. There were many record companies in those days, very famous ones, because the records were being sold in millions actually in those days. And you know, the name Grammy actually comes from gramophone, the Grammy Awards. And these companies like Universal, Sony, Warner, Columbia, many of them actually exist even now. Atlantic, RCA, Capitol, HMV. So HMV maybe will bring back memories to us, to many of us senior people, because HMV was one of the major brands in India. And what HMV means is his master's voice. So the story is, actually there was a dog which found the voice of his master coming from this gramophone, and he was astounded because he could not see the master, but his voice is coming out. He recorded and played back. So the dog was he always used to go and sit in front of this gramophone whenever the master played this. So one painter, a German painter, forget his name, he painted this as a picture, and then he tried to sell it to Edison. So because Edison was making phonographs. But Edison did not buy it. He thought this doesn't carry much value. But then Berliner, when he was visiting Germany, the same painter went to Berlin and asked him, do you want to buy this painting from me to use as a trademark? He immediately bought it. So this trademark originally became Berliner's own, but then, you know, it changed hands many times because all these companies get bought, resold and all that. So finally, even different record labels used to use the same trademark. Like as you can see here, RCA Victor. RCA Victor was the biggest record label ever. They sold the maximum number of records. They were US based. They used the trademark, and HMV itself also used the trademark. Now this is the turntable. I mean, this is the turntable or the record player. And the way it plays is you have a head. So this is the head part. There's a head shell, there's a cartridge, and then the stylus. The stylus is actually made of diamond or something, some metal like that. So this is the cross section, the cross view of the stylus. You can see the stylus here. And in this particular one, it is elliptical, it is diamond, and it's a magnetic pickup. I'll show you that. The cantilever is aluminum, and trackability is 70 microns. So the trackability is very good. And here you can see how it works. So the stylus is here. The stylus moves through the groove recorded on this. And so there's a cantilever here, and the magnet, there's a small magnet. It moves. When the stylus moves, the magnet also moves. And then there's a coil here. So when the magnet moves, there's a current induced in the coil, and that current is then amplified. And finally, through the amplifiers, it comes out, and that's what we get at the output. So the types of stylus, sorry? For the stereo, there will be 2.
You'll be
Yes.
another coil.
Exactly something that is similar. Yes. 2 coils and everything twice, 2 times. So, yeah, there used to be different kind of needles, mostly 2 types. One is the magnetic kind of pickup, the other is ceramic. Ceramic is the old one, gramophone kind of thing. And so in the magnetic pickup, we use only diamond, but in the ceramic, we use diamond and also sapphire. So they were spherical in shape, but for the diamond, actually there were different shapes. So the shapes were chosen such that you get maximum lateral swing, and also, it stays well in the groove. Actually, even after all this technology, sometimes when they make records, they make mistakes. I still remember this very famous movie, Shankarabharanam. So it was made at a very low budget initially. So they actually gave the job of making the records. In those days, I think cassettes were just coming. It's still records. So the contract for making those audio records was given to a fairly new company. And when they cut the records, their grooves were shallow. So what happened was, it used to skip. So I know this very well because I used to play these records in the hostel. I was the mic man of the hostel when I was doing my BSc. So we used to play these records and the needle would just skip, just like that. So after this, later, when the movie became a big hit and they had a lot of money probably, and then they changed. That's the story. I really don't know exactly, but this is what we heard in those days. So the company was changed and then they issued new, much better versions of those records. So this is something that one needs to be pretty careful about. So that was the time of records and all that, and now we come to the era of tape, magnetic tape. So this is the original, the first studio and home kind of reel-to-reel tape. It's also known as the spool tape. So sound was recorded magnetically on these tapes, and then using the heads, appropriate heads, again coil type, magnetic pickup. So those pickups could be used for replaying these sounds which were recorded on these tapes. So those will remember, the oldies will certainly remember these TIAC and those companies, Technics. So all those companies had very good, excellent double-deck record players and recorders and all that. They were very good pieces of manufacture, and they still exist with many people. And even though cassettes are not coming anymore, people who have cassettes, I still have a few. So these are the cassettes, as you can see. So for the younger guys who may not have seen this, so we can play them. I also have a double deck at home, which is not much used anyway. So these are the cassette companies, TDK, BASF, and all those companies of those days. And there used to be demagnetizers, because when the tape runs over the head for long times, like when you run it for 3 months or 6 months, it is a good idea to demagnetize the head. So you could run this tape just like that for half an hour for demagnetizing the tape, the head. So this is the tape head. So it will look like this. So one can actually, in those days, you could buy the tape mechanism and you could buy the tape head, everything separately, and you could fix the tape head in the mechanism. I've done all these things in my younger days. So, and then you also need a preamplifier for this. So again, this is magnetic pickup, as you can see here. And it is very important that because these signals are very, very small, like only a few millivolts, that's what you get from these tapes. So you have to amplify them right there itself. And this cable has to be small. You cannot have a very long cable because a lot of noise pickup will be there. And this IC was very famous for this purpose, LA3161. So that was the IC that you would use for making a tape preamplifier. I still remember, I may have some boards with me. So that was the time.
Mention the important role of pencils.
Important role of?
Hexagonal pencils.
Huh.
The pencils.
Yeah. Oh yeah, the rod of pencil, absolutely. Yeah. You had to wind it, rewind it sometimes. So you would sometimes it gets stuck. It gets stuck. So you have to really use a pencil. The pencil was the right size for for turning these tapes. Yeah, exactly. Thanks for reminding me. So yeah, we used to do all those things in those days. And in those days, there were things to do, I mean, unlike now, where everything is streaming and you just sit in front and you push somewhere, you get songs. It was not like that in those days. I mean, it was more involved. But anyway, things change. So now this is the radio. So radio was another instrument of a lot of entertainment in those days. And we had all kinds of, again, very nice looking, good looking radios. I'm sure in some of your houses, maybe these things exist even now. And if you have, then remember, these things are fetching a lot of money now. So if somebody comes to you and asks you, can you give me that old valve radio for 50 rupees? I'll take it. Don't give. Because if you look, the kind of prices this is being sold now, it's in 10,000s actually. Just look in eBay or something like that, 5,000 and above. Most of the, even in non-working condition, there are people who will take it. So anyway, so these radios had very interesting things like magic eye and all that. This magic eye was a kind of for tuning to a certain station. See, now everything is the push of a button. It goes straight away to the station and it gets locked there. But it was not like that in those days. You have to really turn something and then, correctly go to that station and be there and all that. So this magic eye will help you find the station properly. So it's a band of light like this. It's a valve or a tube. So there's a band of light there. So when that band becomes very narrow, the narrowest possible, you have tuned exactly to the station. So this was the way they worked. And different shapes and dials and everything. This is a newer kind of, a new radio in comparison. So these are the valves which were being used in those days in these radios. And so there used to be 2-3 different bands. So this is the low frequency. I haven't really seen the low frequency band in India here, but this exists in some other countries. And the medium wave was quite popular because all the local radio stations were in medium wave. So that extended from 526 to 1706 kilohertz. And then there was a short wave. And it was in the short wave that all the international stations were there. Because the short wave frequencies from 3 to 30 megahertz, so that is where, these frequencies can get reflected from the ionosphere. And therefore, you can have a shortwave station here, and it goes, can get reflected in the ionosphere, and you can hear it in Europe, for instance. That kind of distances could be managed. So like BBC, it's still possible to hear BBC in shortwave here, which is transmitted from London, actually. Not without any repeater. So that's the advantage of shortwave. And many radios actually divided the shortwave into multiple bands because, there are 8-band radio, 10-band radio, like that you hear. So whatever you hear, the division is always on the shortwave because, radio stations were crowded in the shortwave, all the international stations. So that's why it was like that. And in those days, actually, we did not have, in my childhood, India did not have a satellite for communications. It did not have even a single satellite for anything. So the first ever satellite was Aryabhatta. And I think before that, the country hired some other satellite, some foreign satellite for communication. And there was the news in the newspapers. So until that time, the news, all the local news, Malayalam news, Tamil news, everything used to come from Delhi. There was a centralized news there coming from Delhi. Or the national news was coming in that, and the local news was coming from the local stations. So I remember at 7:25 a.m. the morning, the Delhi Malayalam news used to come. So this was extremely noisy in the radio. You can hardly hear it because of all the noise and not because of the LED noise now. Remember, there were no LEDs, nothing in those days. The noise from the atmosphere was practically nil in those days, but the noise was simply because this was coming through multiple repeaters from Delhi all the way terrestrial. It is coming through maybe 10 repeaters or something, and along the way it accumulates a lot of noise. That's what's happening. And then it was in the newspaper that from this particular day, the news, India will use the satellite for communications, so it will be clearer. So we just read it, that was it. On that particular day, switch on the radio because at 7:35 we had to go out of the house for catching the bus, school bus. So you don't really look at the clock. You keep the radio on so you know the time, continuously you know the time. At 7:25, the news came from Delhi, crystal clear. We were surprised like anything. This was the first experience of something hearing clearly through the radio. So much clearer than the local stations. So that was the effect of the satellite. Now we don't even remember these things because, I mean, you are all born into the era of satellites and you never experienced these things in your life, many of you. So anyway, and Radio Ceylon was there. I'm sure some of you might remember Radio Ceylon Ceylon is the previous, I mean, now Sri Lanka. Ceylon was the name earlier. So Radio Ceylon used to send out programs, half-an-hour programs in Tamil, in Malayalam, probably in Kannada also, I don't know. So it used to send, and it was very wavy actually. At this moment it's loud, the next moment you cannot hear anything like that. So, and these AM stations which radiate in the microwave, they have big antennas. So maybe you have seen, some of you, when you travel along the highway side or something, when you see a radio station of the old kind, not the FM stations by the way, I'm talking about medium wave stations, they have very tall antennas like this because the length of the antenna is dependent on the wavelength, which is larger for medium wave, and this is called the mast radiator for medium wave stations. This is a radiation pattern. And so same case with TV also. So there was no dish in those days, no cable in those days. So you have to catch the TV signals using antennas. And the TV signal is usually very weak because you don't have TV stations everywhere. And you had to use antennas called Yagi antennas in those days. And you have to erect these antennas on top of buildings. So in villages like ours, I mean, you don't have an apartment building or anything. A house is here, then the other house is quite a while distant. So you have to use some of your trees in your compound to actually erect the antenna. So people used to do this. You get some laborers and they will go up with the antenna and then fix it there. And some of you might remember these things and all those things. And then you have to turn it. So this is a big business. You keep turning the antenna towards the station and somebody has to say from behind, got the station, got the station. It's like that. So when you get the station like that, you fix it there. So this was a lot of a very interesting exercise in those days. And we had solitaire TVs, and then I forget the names. Which one? Telirama. Telirama. Okay. Yeah, solitaire, yes. Yeah. All those things were there. Yeah. Some Dine was there. What was it? I forget. And then the other TVs were imported, foreign, Grundig, and all those guys were there. Yeah. So these were the TVs of those days. All those companies except Grundig, I mean, it's of course a German company, it still exists. But the other Indian companies have, I think, vanished or merged with some other companies. So these terrestrial channels, actually, they broadcast in channels between 52 and 600 megahertz in the VHF and UHF bands. And it can travel by line of, it travels by line of sight actually in this frequency range, and because it's high frequency. So it can get up to 60 or 100 kilometers sometimes, and depending on the conditions, atmospheric conditions, sometimes this could be even, it could travel even longer. So this is the Yagi antenna. So it has a driven element, which is called the dipole, and a reflector, and then several directors in front of it. There are various flavors of the Yagi, and one can use, there are multiple Yagis you can put on the same mast, and composite antennas of that kind, which is very useful for when you want to look at multiple stations, when you want to tune to several terrestrial stations. And then there are antennas for mobile phones also. Now these things are available in Amazon and Amazon. So I don't know how well they work and all that. But of course, the mobile frequencies are much higher, so therefore the antenna size also becomes smaller. One can buy them and maybe try it out at home if there is signal problem at home. So not sure about its efficiency, by the way. So this is another type of antenna called the quad antenna. I did a lot of experiments with the quad because for getting TV and FM radio signals at my home, and it worked also. And my best experiment was using the poor man's antenna, because when I was doing my postdoc, it so happened that from my window, I could actually see the TV station, the local TV antenna. And this is the actual photo of that TV tower. So I was at line of sight. I could just see it like that, although it was some 10 kilometers away, something like that. So I used the metal hook, the hanger, shirt hanger. You just remove this part, just cut this side. It becomes a dipole antenna. So poor man's dipole antenna, and I got some 7-8 stations like that, just pointing it towards the. So I could save quite a bit of money that way. Otherwise, I had to take a cable connection. That was the only possibility otherwise. So I could save some money. Postdocs are always poor, so you cannot spend a lot of money. So yeah, so antennas also had booster circuits. So preamplifiers for antennas were there. You could buy them for 400, 500 rupees, and these had to be fixed on the antenna itself. Again, because of low signal amplitudes, you cannot. And in some of them were actually you had a unit down there near the TV that was just the power supply, and the real preamplifier was sitting near the antenna at the top. So, and they are common base amplifiers actually, because these are current followers. So therefore, it's not a common emitter configuration. All these were actually common base kind of amplifiers. And now we have satellite, of course, TV, both TV and radio over satellite. So dish antennas, there are the C-band antenna is the large one, and the Ku-band antenna are the smaller one. So nowadays, we don't use the C-band dishes. For all home purposes, this is the Ku-band dishes, the small dishes that we use. And there are free-to-air channels. So in case you don't know about it, we know only about paying for the TV channels and paying some company and watching the TV channels. But all the Doordarshan channels, all the Akashvani channels, they're all free, actually. If you are willing to set up an antenna on your own, which is something possible to do, in fact, that would be a very good exercise for you younger kids here. So what you need to do is to buy a dish. I think one could buy for 300, 400 rupees. Then an LNB, another 150 rupees. And then, a satellite finder is good. So that will cost you maybe 400, 500 rupees. And then you need the STB, the FTA, free-to-air STBs are available. So there's a brand called Solid. So this is a Chinese brand. Solid sells for 1,200 rupees or something, very good FTAs with HDMI connection, for example. So once you set up all these things, you just need to point your dish in the right direction, and all that information is available in the net. For us, most of the satellites are in the southern sky. So that is why when you look at all these dishes, they're all looking towards the southern sky, actually. So just point your dish to the appropriate direction, the angle, and also the azimuth, and use the satellite finder. When you catch onto the satellite finder the needle will move, and it will also make a tone. So then you are actually caught onto that particular satellite. So INSAT 4B, for example, used to be the satellite from which you could get all the Doordarshan programs and radio programs. I actually set it up in my helicopter. Maybe you remember, in front of our house, on the ground, there was a dish pointing towards the southern sky. It was actually looking at INSAT 4B. So people used to ask, why are you keeping a dish on the floor? It is supposed to be sitting on the top of the terrace. So I said that this is the purpose, it's not. So something set up by myself. And then the bandwidth of radio and telephony. So radio is like the AM bands have only a bandwidth of about 10 kilohertz, because they're not really supposed to be very high fidelity. So you need at least 20 kilohertz for proper high fidelity, but the AM bands in the medium wave, they don't have that kind of bandwidth. But in the FM band, this is not at all a problem. FM bands usually have intervals of 50 kilohertz at least, because 88 to 108 megahertz, you have a lot of bandwidth there for radio. So they are well separated, and also a lot of bandwidth in the along with the carrier. So that means that is the reason why the FM is very, very clear and it's superior to AM transmission in quality. Of course, all of us know that the FM is of very good quality. This is the reason for it. Okay, so now let us look at the digital era. So I was talking mostly about the analog situations, and now we have come of age into the digital era. And so what are the changes there? So first of all, what is digital stuff? So signals by nature are analog. So because they are not made in pieces, right? Signals are continuous, they are analog, but when you convert them into the digital domain, that is when you sample them, when you get small pieces, chop them out, and then the greatest advantage you have is that you get the ability to process your data. In the analog domain, processing is not very easy. You are very limited with your processing. But in the digital domain, there are various things that you can do. For one thing, the noise can be reduced a lot. So that's why the CD is much more quieter compared to a tape, for instance. So this is what is done. Everybody knows about A to D conversion, so I'm not really going much into this, except to say that if you take a 10 kilohertz raw signal like this, and then consider that you are making a CD out of it. So for making a CD out of it, you have to digitize it first, and this is the way you will digitize. See? That is the way you digitize for CD. Because the CD audio, the rate is 44.1 kilohertz. It just meets the Nyquist criterion, which says that when you want to sample an analog signal, you have to use at least twice the frequency of the highest frequency contained in that. So therefore, the highest frequency any audio signal can usefully contain is 20 kilohertz. Beyond that, it's no use. So therefore, you have to sample above 40 kilohertz. And for some reason, for the CD audio, the sampling frequency is 44.1 kilohertz. And, but DVD audio, you can sample this for making a DVD audio, and then you actually sample this at much higher frequency. It is like 192 kilohertz. So you can see the difference here. Just imagine, after sampling like this, when you reproduce that back into analog signal, which you need to do anyway, just before the speakers at least, or before the amplifiers, you have to do this. When you do that, you won't be getting the original signal. So this is a problem with digitization. So we can see that the number of and not only that, for the CD, while the resolution is 16-bit, for the DVD, the resolution is 24-bit. It makes a huge difference. So therefore, when you sample for CD, you can have number of possible output levels, voltage levels are 65,000 and odd, but compare that with that of the DVD. DVD is much, much higher than that. So therefore, naturally, it is easy to see that when you want to digitize audio, compared to the CD audio, the DVD audio will be certainly better to hear. But then there are, of course, limitations everywhere. So digitizing at such a high rate may not be always possible, may not be always economical also. So all these things are driven by economics, the profits of companies and all that. Companies decide which technology should exist and which technology should die, irrespective of whether it's the best technology or whatever. So all the market forces, everything are there in the play here. And coming to video display standards, again, I mean, there are great demands. Like if you look at ultra high definition, that means 3840 pixels horizontally and 2160 pixels vertically on the screen. So if you take a 56-inch TV, this means that on every centimeter, you have to have 30 pixels minimum. This is kind of back of the envelope calculation. I haven't really taken the real dimensions of the 56-inch TV. So this is roughly the number. It's not the exact number. So you can see this, and each of these pixels need to be addressed individually. So therefore, you can imagine the kind of data that you need in a DVD or even for transmitting in 4K. So data storage capacity, so for the DVD is much higher. So this is how it is done on the CD. And for the DVD, you can see that all these patches, they are smaller in size. And also, then finally you have the Blu-ray. The Blu-ray is the thickest, probably, physical medium that you can have now to contain data. The Blu-ray disc can actually contain data. I have Blu-ray disc here. So it looks exactly like a CD. So see, this is remastered, The Sound of Music, the classic movie, and there are 2 discs inside. So it's a long movie, actually. So more than 2.5 hours or something. So 2 DVD discs completely contains the remastered high quality video plus 5.1 Dolby Digital audio in that. So, and the Blu-ray works at violet light actually, not at blue. So 405 nanometers. So that's a kind of the laser diode that you use, that you have to use for reading a DVD disc. Smaller wavelength. HD DVD. That's quite possible because it's quite possible. In the HD DVD, it's quite possible. Yeah. But then the advantage for the Blu-ray is that the size is little smaller, 150 nanometers, so it can contain more data. Yeah. Now, this is actually one of the issues with digital recording. Digital recordings can be compressed. So that's the boon and also the bane of this technology. So what happens is you can have uncompressed data. So if you use uncompressed data for whatever you do, I mean even for watching a movie at home, then you get the maximum resolution. But this is not always possible for various reasons. So people compress. So this is, I'm talking only about audio. If you see this logo somewhere, that means it is uncompressed audio. Compact disc digital audio. If you see this, FLAC is compressed, but it doesn't lose any data. It is compressed, the file size can be half of the original, but it doesn't lose any data. That is free lossless audio codec. But if you see MP3, that MP3 can be heavily compressed. There are various degrees of compression in MP3. So people who actually use MP3 and who have an ear for the musical perfection, they say that if you have 128 kbps, if you have that kind of MP3 recording, then this is okay. It is acceptable. And if you have 256 kbps, that is perfectly okay. Beyond 256 kbps, if you actually make an MP3 recording, it is not really going to make much of a difference for our ears. So that much of compression is fine. But sometimes, people compress too much. But at least here, we have a choice. If we have the original CD with us, and if we want to make the file size smaller, then we have the choice to compress to the level that we like. It is possible. And then digital audio signal processing, a lot of things are possible in the studio and also on the stage. So distortion, actually, unfortunately, I cannot play these things. I have many hyperlinks, but I cannot play them. So in guitar, all the guitar players, they actually distort the sound intentionally when they perform on the stage, even in the studio. Because for some people don't really seem to like the real pure guitar tone. If you distort it, it adds a lot of flavor to the rock music and all that. So it can be intentionally introduced. And in fact, many guitar players actually use tube amplifiers or valve amplifiers because the valve amplifiers introduce a distortion which is very smooth, unlike transistor amplifiers. So we will look at it later. So there are lot of effects that you can have using guitar pedals because the pedal is down there while the player is playing with his hands here. He's actually using his legs to press on various things. You may have 4 or 5 different stuff there. So he chooses which one to press and then he presses accordingly, and that's what he does on the stage. Now, this is something which is very detrimental to music. This is called dynamic range compression, and sometimes it's also referred to as the loudness war. So what happens here is the following. See, because the ear is capable of hearing from very low levels to very high levels, if you have a symphony orchestra, for example, There are moments when there is absolute silence. Then there are moments when there is a huge sound in the auditorium. Your ear can accommodate that. Now, can your amplifier accommodate this? It's a question. Well, the good amplifiers can accommodate this to a good extent, but the problem now is that nobody these days uses an amplifier and proper speakers for listening music anywhere. I mean, there are only very few people who have the bigger speakers at home anymore. Whoever had them, they sold them off to somebody. And because now everyone is hooked to the mobile phone. And when you want to hear music from the mobile phone, there are only two possibilities. One, you hear it just like that. The second, you put an earphone in your ears. Now we know that earphones are such small devices. The dynamic range is very, very limited. So they just cannot go. The so limited earphone, how can you hear the entire passage of music? Imagine hearing a symphony orchestra through the earphones. So the people who record these things, now the recording industry is recording for the mobile phones. They are not recording for big amplifiers or big speakers. So therefore, they intentionally compress the dynamic range. So what they do is, they increase the lower levels, they give amplification there, and they decrease the top. So something that had this kind of dynamic range now gets compressed to this range. And then you will hear everything through the earphones, but what you hear will have a lot of distortion. It won't actually hear like the original, so that's the difference. So this is the problem with DRC, but companies do it. They do it so much that many people are very critical about that, but there is nothing much one can do because it all depends on what kind of devices you use. There are, of course, websites like Meena and Sujata told me about Spotify, where you actually get high definition audio. So you can get high definition audio there, and you can play it. Certainly, you can defeat DRC to some extent, because the recording itself is like that. Okay, so now we will go to the systems and circuits. I'll do it fast. So the components of an audio system, you have the inputs here. There are various inputs. There can be various inputs in the olden days, but now there is only one input, either the laptop or the mobile phone, nothing else. Anyway, so the preamplifier, then the power amplifier, then the crossover at the end, where the frequencies get divided before they go to the speakers. So this is a more modern kind of picture. This is the old picture. So here, Wi-Fi, Bluetooth, those are the inputs. They're all high level, by the way. The signals are at high level. Then processor, then DAC, digital to analog converter, then audio amplifier, the speakers. So power management. So looking at the preamplifier, I'll not go into much detail here because of lack of time. So this is taken from one of the very, very interesting pages. You can, if anybody is interested, you can actually go and read the articles in sound-au.com. There is this very celebrated guy by the name Rod Elliott. Actually, I had the good fortune to meet Rod in person in many years back in Sydney, and so we had a good discussion for about an hour at his home, actually. So he's a fantastic person, knows so much about these things, and so he has produced many circuits, and this is one of the interesting circuits that he has did. So there is several inputs can be chosen here for the preamplifier. Then there's an input buffer, tone controls, then finally balance volume. So these are the things a preamplifier should have, tone control, bass, treble, or an equalizer, and volume control, balance control. So these things should be there on the preamplifier. So this one is a very good one at that. And then, well, of course, I mean, this is a circuit, the same circuit actually, that preamplifier circuit. It's available in this form. You can buy it just like that. And then, this is a tube preamplifier. And this is from Marantz. Marantz is a very well-known company, and they have produced a lot of interesting stuff in the past. Even now, they do. And this is a preamplifier offered from Marantz of vintage. Okay, so this is from Macintosh. Macintosh is another very, very well-known company for audio. And back side of this Macintosh unit shows so many inputs. So you can, there's a lot of flexibility here. You can try various, several inputs can be given and all that. It is all possible here. So they also have the digital audio inputs. This is a reasonably modern Macintosh product. Now coming to the power amplifier. So after the preamplifier, you have to have the power amplifier to drive the speakers. So this particular one, it's a very, very standard topology of the power amplifier. So there are 3 stages in this. The first one is the input stage. So the input stage here is a differential one, as you can see here. And it has a current source here, so that the current, the bias current in the input stage is controlled, very well controlled. And then after that, you have the voltage amplifier stage here. So that's the voltage amplifier. And in the collector line, you have the bias control. So you have to set the bias for an amplifier. So it should not be too high. If the bias current is too high, then the output transistors will get. By the way, I'm only talking about transistor amplifiers, because even in the IC, this is what you have. So, so the bias current needs to be at whatever minimum required. There's no need to increase the bias current beyond some limits. It only heats up your transistors. So that is the VAS, the voltage amplifier stage, and then you have the output stage. In the output stage, you have the real big transistors, which actually have they take up all the current. So the currents here are very small, but the currents here can be substantial. And then you connect to the speaker. This is what you do. And you apply global negative feedback. I'm sure everybody knows about negative feedback, because that's very important for the stability of the amplifier. If there is no negative feedback, the amplifier will oscillate. So there are models which use minimal feedback and all that, but there are various topologies. Now again, from Rod Elliott's website, so this is a very, very well-known design of his called the P3A. Actually, the P3A is here. This, when we will do the demo, this is a P3 amplifier here. And so we made that, and as you can see here, it's not too many components. The same, very similar topology, you have the differential input here, and most of the other things are like that. I'm not going into those details now. Now this is another, shall I say, venerable amplifier topology, because it's very old, from the 1970s, and we have these amplifiers here. So, and the interesting thing, this is very interesting. This amplifier topology is inferior to the previous one in almost every count. So I'll tell you, I have to tell you this. The input stage is singleton, which means it is not a differential input stage. All of us know a lot about the differential input stage and its qualities and all that, but this is not a differential input stage. Now the voltage amplifier stage, VAS, has a small Miller cap. Now believe me, this particular capacitor here, unfortunately I don't really have the time to explain to you the circuit. This small 27 picofarad capacitance here, it determines, that's the dominant pole of this amplifier. It determines your high frequency response. If I double that, I mean, it's such a tiny ceramic capacitor, 27 picofarad is nothing. If I double that, the character of the amplifier will completely change. Whatever I do, it will sound very dull. So the value of this Miller capacitor is extremely important in the entire amplifier topology. Now, what is important here is that this singleton input has inherent stability, and therefore, in the previous one, with a differential input topology, we have to put larger Miller capacitors. The moment the value of the Miller capacitor goes up, like in the previous one, there were 2 Miller capacitors, each were 100 picofarad. Now this is 1 and 27 picofarad. This is what makes, in my opinion, the whole difference in these amplifiers. So Meena and Sujata were doing this amplifier, and finally, when we played each one, we played the P3A, we played this, and I asked them, which one do you like? They immediately said they like this, without really knowing much about the circuit or anything. Right? I never told them this is a singleton, this is considered to be an inferior circuit, but actually in practice it is not. In practice, it's a very good unit, and the output is quasi-complementary, which is again considered inferior. The output is capacitor coupled. It's a strict no-no for many new designers, but after all this, that amplifier sounds better than the previous amplifier. So this is why in audio, we have a lot of subjective experiences. On paper, you have circuits, and obviously you can calculate the distortion, you can do anything, and you will see that this particular circuit is better than this circuit in every respect. But when you actually try it out in practice, sometimes it so happens that the supposed to be inferior circuit actually plays better. You have better hearing pleasure from that. So these things people discuss many times. And these are commercial amplifiers, you know, the backside of several connectors and all that. Coming to the loudspeaker, I hope to finish in another 10 minutes or so. You need a crossover for the loudspeaker. So this is the passive crossover, which you connect just after the amplifier, before the speakers. So a single speaker driver is usually not, it's never capable of reproducing the entire frequency range from 20 hertz to 20 kilohertz. It is impossible for any single speaker to do this. So that's why we need to divide this into 2 or 3 speakers. So here, for example, in this case, I mean, there are some efforts to have full range speakers, for instance. So people make, I mean, like, you know, there is a big cone, and on top of the big cone, you put a smaller cone. So the big cone takes care of the lower frequencies, and the smaller cone takes care of the upper frequencies. So these are all some compromises, which may not really work that well. So Fostex is a good company, and they have, and many other companies actually have full range speakers. They have their advantages though. The greatest advantage of the full range speaker is that there are no phase issues. With any 2-way or 3-way speakers of this kind, like where it is all divided. See, there is a woofer here where the output is low frequency. There's a mid-range where the output is, I mean, you have a bandpass filter, and you have taken the central regions of the audio frequencies, and in the tweeter you have the high pass. So this is the way it looks. You will have inductors, you will have capacitors in this thing. And here you see the characteristics of low pass, high pass, and band pass filters. Notch we don't use in audio. So there are also phase relationships. I'm not going into the details. So the structure of a three-way passive crossover is something like the following. So let us say you have an amplifier output like this, a complex signal here. So this complex signal can be divided into 2 or 3 frequency bands like that. And then the low pass goes like this to the woofer, high pass to the tweeter, and the band pass goes to the mid-range. So that is what is done. And the frequency response of higher order filters, you can have several orders of filters, first order, second order, third order, like that. The higher order filters will have this kind of a frequency response, a sharp fall off, a roll off. And also, you can see the same thing there. And the phase response, so that's also important. When the order goes up, the phase change, there is a phase change at the crossover frequency. So the phase change is more sudden, or it's more abrupt in the case of the higher order filters. So therefore, you have to have kind of compromise, because you know that your speaker drivers cannot really reproduce all the frequencies. So therefore, you would naturally think that, okay, if I take the sharpest filters, which mean, if I have the higher order filters, 4th order, 6th order, something like that, then I will match my speakers exactly, so I should expect the best results to come. Actually not. The reason is the following. With this kind of a large phase variation in and around the crossover frequency, what will happen is that the different component frequencies will travel at different times. So this is called a phase delay or group velocity dispersion. So with this group velocity dispersion, what you get at the output is distortion. Because in the recording studio, a certain sound has been recorded, and now after doing this kind of filtering, you have really spread that sound into a longer thing because of the dispersion. So you are not really going to hear. So the effect of this in practice, because I've tried 4th order Linkwitz-Riley filters and 2nd order also. So I've decided that 2nd order is better, because in the 4th order, it is very clean, clinical, people say clinical voice coming out of the amplifier, but there's no punch. There is no soul to it. It's all gone. So one has to hear this to understand this. Although it's very difficult to explain this. So that's the way it is. So people usually settle onto second order filters. I like first order, by the way, but as a compromise, go to second order. So, okay, this is a frequency response of typical speaker drivers, the two-way, three-way, and all that. And the subwoofer is very important because, as you can see here, down here there is sitting a subwoofer. So the subwoofer makes all the low frequencies. So for this one, the frequency roll-off is cut at 130 hertz, but it came to 100 hertz actually, 110 hertz. So this is the response of the subwoofer. And this is a two-way speaker where you have a woofer and the tweeter. And this is a three-way speaker where you have the woofer, the mid-range, and the tweeter. Now, three-way will appear to be better because, I mean, you are dividing more, but in practice, my experience is that it's not really very easy to set up a three-way speaker properly. One of the reasons is that you will get woofers and speakers of reasonably good sensitivity, but somehow the mid-range speakers that you get have low sensitivity, and somehow I don't know whether it's my problem. You will see three drivers here. This is the woofer, this is the mid-range, and this is a speaker, this is a tweeter. Actually, this is not running. It is sitting there just as a dummy. So we have to cross I originally built it as a three-way, but later decided to go for two-way. So only this and this are working now, not the central one. So that's the way it is. And this is a 2.1 stereo system. And 2.1 means two channels, stereo channels left and right. The 0.1 is always the subwoofer channel, the low frequency channel. So you can see left, right, and the subwoofer sitting here. And passive crossovers, as we have seen, I mean, in fact, in reality, it looks very simple, but the real passive crossover to sound the best, it has to be more than that. So there are more things like baffle step compensation, time alignment correction, and all that. So if you don't do all those things, the effect of your passive crossover will be limited. So at least that's what the theory says. So even though I don't really feel it in practice much. Now therefore, one can have active crossovers. So this is a second order, that is 12 dB per octave, Linkwitz-Riley configuration, active crossover. So this circuit you actually place in between the preamplifier and the phone amplifier. In other words, in between the laptop or the mobile phone and the phone amplifier. So when you do that, you can control the frequency characteristics of the filter. So high frequencies come here, low frequencies come there. And then you have to use different amplifiers so one amplifier for the high frequency, one amplifier for the low frequency. Now considering that in a stereo system there are two channels, you will need 4 amplifiers in total. So that is the drawback of this. Having 4 amplifiers is very expensive unless you make all that by yourself. So we did this in the lab and also measured their frequency response. So we designed this crossover for 130 hertz to run that subwoofer, and we got a final value of 110 hertz. So this is because capacitor values have large tolerances. So what is printed on the capacitor may not be the right value of the actual capacitor. This is the reason why you have this kind of difference. And so this is the system that we will demo here today. So your source is here, then active crossovers for either channel. High frequency goes to the Philips amplifier, 2 of them. The low frequencies are summed. So we use an op-amp adder here to sum those 2 low frequencies because low frequencies are not very directional. They can spread over the room, so you don't really need 2 subwoofers. So then it goes to 1 sub, and then the passive crossover is cut for 1200 hertz. So what comes out here, the high frequency, it is again cut into 2 using a passive crossover. So 1 active here, 2 passive here. And this works very well, actually. So power supply and grounding, you need to be careful. I have no time to discuss. And surround sound systems, you have Dolby Digital, DTS, all those things. And this is how surround sound is encoded on film when film was used in olden days. Now nobody uses the movie film. And this is the RRI auditorium setup. So we actually have a surround sound setup here. And so the subwoofer, have you seen the subwoofer anywhere? Where is it? That's the center channel. So you have the left, front left is there, front right is there, center is there. So back left, back right, surround back left, surround back right. Where is the subwoofer? Jacob knows. It is here. You can come and look. It is hiding here, the big one. Okay. So this is our setup, a full surround sound setup. So if you want to make one home theater at home, there are various ways of doing it. So, well, I mean, it can be pretty expensive. If you want to do it cheap, you will not get all the 6 channels. See, in Dolby Digital, you have 6 channels. If you want to properly reproduce all the 6 channels, we really don't have much of economic options. Some money needs to be spent, but of course, it is cheaper than if you buy something, you can make things at home. So I would say the program source is here. The HDMI output needs to be taken. And a projector like eGate, I mean, I'll show you that projector. These things are available. These are very expensive projectors, but you don't really need them for home. You can buy projectors from rupees 7,000 upwards. And for rupees 10,000, you can actually get a very good projector. Only thing is, the brightness of the projector is nowhere near that of an LED TV. So the LED TV, you can watch a movie in this kind of light here now. I'm not talking about this projector. It is very bright, but you have to pay so much for it, lakhs. So this is about the 10,000 rupees projector. If you want to watch a movie, do it after 7 o'clock in the evening. Or if you have a room that can be properly darkened, you can watch any time during the day. But if you watch in the night, it is exactly like a movie theater. I do it. That's why I'm not watching too many movies, but when I do, I like it because it's like a movie theater at very low cost. The screen part is, the projection part is not very expensive. You don't even need a screen actually. The screen, the automatic screen will cost you maybe 10,000 rupees, but if you have a fairly well-painted wall, that is sufficient as your screen. That's what I do. The money goes on the audio part, not really on the video part. When you want to reproduce all the 6 channels, and if you have Dolby Atmos, by the way, Atmos has height channels also. So there are at least 2 speakers top there. So 8 channels. So if you want to reproduce all that, you will have to use a receiver, AV receiver, and the AV receivers are expensive. So this is something where one has to see how much money you can spend and then decide accordingly. So this is what I use. So this is my projector at home. You can see it fixed from the top, hanging there. And this is an Xbox, which is used for streaming videos and movies and all that. So from the Xbox, the HDMI connection goes to the projector, and the optical or SPDIF, that connection goes to the audio, the receiver. This is a receiver, and this is a Blu-ray player. So this actually works very well. Okay, coming to the end of this talk, what are the recent trends in hi-fi audio? So we have seen what has happened in the past and what's the current trend and all that. But even those are getting changed, and now for home audio, actually people are going back to these records. It's a comeback of the turntable, which had completely disappeared, by the way. They're coming back now, companies are making, and also the valve amplifiers, preamplifiers. So I had a visit to this showroom, Magnolia, in 2012. It's a Seattle-based company and had a very good experience there. I will say that in the next slide, actually. So look at this thing. It looks so nice, right? But this is a model from 1961. It's a Macintosh model from 1961. So now people like the lighter tubes, and the transistors are not colorful, right? These tubes are very colorful, and they make it like artistic pieces now, and that is one reason people like it. There's also another reason, because the sound is very warm. So, the thing is, analog record discs, in principle, they are analog and they are lossless, in the sense there is no compression on them. But in reality, all the discs which are being pressed now, being made now, they are made from digital masters. Because there's nothing that escapes digital these days. But the good thing is, when the digital master which you have in the studio is excellent, I mean, it's a fantastic piece. It's like original analog. That is used without compression for pressing these records. So therefore, it is as good as lossless audio. That is number one. The second thing, almost always when you use a turntable, you use a tube amplifier, the valve amplifier along with it. So the valve amplifier has some advantages. The valve, for one thing, the distortion produced by valves are predominantly even order, second order, fourth order, like that. But the distortion produced by transistor amplifiers is mostly of odd order. That's a third order, fifth order, like that. This is because of the symmetry of transistor amplifiers. Not going into details. So the third order, fifth order, that kind of distortion, harmonic, is not really very good to hear. Particularly when the harmonic order goes up in number, it becomes more and more irritable. So another thing is, the transistor amplifier needs to use lots of negative feedback. When a lot of negative feedback is applied, what comes along with that is the odd order distortion, the higher order harmonics. So one has to strike a balance. The designer has to do a perfect job to get very good sound out of it. But in comparison, the valve distorts very gradually, and most of the distortion is second order, fourth order, which is musical. So it adds body to the music. It doesn't really distort it in that, doesn't make it unpleasant. It adds body to the music, and therefore people like it. This is the reason why these things are now coming back. They are very expensive also. So I had this experience in Seattle. So this is some, you see that in this picture. Right now in 2022, the revenue from the sale of CDs equaled the revenue from the sales of disc records. So it will go up now. So finally, I will show you a pair of speakers. So, and also tell you 2 sentences about my experience in Magnolia. So I saw these speakers myself, and I heard them playing. And look at the price. That's not a misprint. 55 lakhs Indian rupees for a pair. If you ask me whether it's worth it or not, it's difficult to answer. That's what I would say. Because, see, I happen to be in this shop, Magnolia, in Seattle. I will tell you this, it's a very interesting story. We'll finish with that. So myself and my brother-in-law, we went to, he lives in Seattle. So when I was there, we went there for purchasing. He wanted to buy a TV. So we went shopping and went to this place, Magnolia. So they had some TVs out there, normal looking TVs and all that in the front showroom. So I saw a few amplifiers also there, normal transistor amplifiers, reasonably priced and all. So I started talking to an elderly gentleman who is a salesman. So talked to him about these amplifiers and asked a few questions and all that. After talking to him for 5 minutes or something, he just told us, come with me, I will show you something interesting. So we went with him. So the showroom is like this, open. And there's a door to one end, it's a small door. One would think it's a toilet door or something. He opened that door and we just stepped in. It was like we entered a different planet. What we saw in that room was a big room, maybe 1.5 times the size of this room, or even maybe twice. Completely filled with tube amplifiers, turntables, valves glowing and all that. And looking at the price tags, everything is thousands of dollars. Whereas in the front room, you have $200, $150, that kind of stuff. I told him, look, impossible for us to buy any of these things. We don't have that kind of money. So then he told us, I know you cannot buy this. Seeing you guys, it's obvious, you don't have the money to buy this. But then, he didn't say that exactly like that. He was very nice. So, but I brought you here because I think you know something about audio. Most of my customers don't really know anything. They just come and they buy something. But you have some knowledge of this, so I thought I'll show you the real stuff. So then he took us around. He showed us very interesting speakers, very interesting, beautiful tube amplifiers, And they were playing like, my God, I mean, there's no way to express it. So we also heard these speakers playing. So that moment, the moment I heard them playing, my realization was the following: my goodness, whatever I did for all these years, whatever I made was just crap. So that was the final realization. But then, you know, you have to live with the relative crap through most of our lives, and so that's the way things are, because we can only buy stuff which is affordable for us. So that's the way things are, and thank you very much for, there are many references here which I have gone through, like there's a Phillips book, M.D. Hull, and Douglas Self, a master in audio, and his book. Then Elliott Soundboard, Rod Elliott. Then Nelson Bass, he is a master of Class A amplifiers. He is a firm believer in Class A. I didn't speak anything about it. DIYaudio.com. It's a wonderful website where you can learn a lot from that website. And many of the members, unfortunately the senior members, many of them passed away during COVID time. Excellent people. So Internet Wikipedia. And I have to thank some people very much. Sujata and Meena, first of all, for excellent hardware support. So when I threw all these circuits to them and asked them to make them, they actually did it at record speed, and finally, you know, I mean, things were blowing and all that. So, so we finally managed to have a something that works, hopefully. And then to Rod in particular for a very stimulating 2 hours discussion. And Dr. Joni Isaac is a professor at CUSAT. He actually taught me a lot of things. I mean, kind of my guru in electronics. He actually, these speakers, you know, these speakers were built in 1990. It's older than many of you. So Joni and I did this together. So he taught me many things at that time. And then students who shared my interest in audio, I mean, some of my students, Sujan Sandeep and Smijesh Natarajan. So we were very interested. And faculty colleagues, and we used to have interesting discussions about car audio, general audio, with Arun, with Sadiq, with Ranjini, and all that. So when we were all, I mean, most of us were in Pailikaval, staying in those quarters and all that. So I thank them and my family in particular for tolerating loud sounds at midnight, you know, speakers playing and sometimes transistors blowing and suffering revenue loss caused by fried power transistors. So thank you very much for hearing me for this long, long time. Thanks a lot.